Assalamu alaikum, sir. My name is SM Mashur Alam and my ID is 235175582. Today we are presenting our project for the Digital Logic and Circuit course titled as Digital Parking Control System. This project applies digital logic concept to automate vehicle entry and exit using logic gates and counters. We are Group 8, consisting of 5 members, and everyone contributed to the design and documentation of the system. The parking garage capacity is limited to 7 cars based on the project requirements. In digital logic, the decimal number of 7 is represented as 111 in binary. To handle this range, our system is designed using a 3-bit architecture which allows the counter to track values from 0 to 7. This ensures accurate monitoring of the number of the vehicle inside the parking area and helps prevent overcapacity. Thank you, sir, and I am going to pass my project to the number 2 person.
Assalamualaikum sir, I am Miruna Reza. I am describing encoder block diagram and truth table. To process the inputs from the parking slots, we use an 8 to 3 encoder. The job of this component is to take 8 individual inputs representing the status of parking slots and convert that information into a 3-bit binary output. You can see the relationship between the inputs y0 to y7 and the output is a0, a1 and a2 in our truth table. From the truth table, we derive the logic expressions for each output bit. A0 is the sum of y1, y3, y5 and y7. A1 is the sum of y2, y3, y6 and y7, and lastly A2 is the sum of y4 to y7. We implemented these expressions using OR gates as shown in our logic diagram. This ensured that any time a car spot and spaces. Thank you.
Assalamu alaikum. Myself Shahir Alisiam and I will explain the block diagram of the system. Here we can see sensors detects entry or exit, then signal sends to counter, then 3-bit up down counter, next to the 3-bit people register, next 3-bit comparator which compares the car count is 7 or not. Here we can see some sensors like car entry and car exit. When car enters, it counts count plus 1. When car exits, it counts count minus 1. Then signal sends to compare car until count 7. If count is 7, then displays full. If count is not 7 or less than 7, it displays space available. Then it repeats the process and starts counting to 000. 3-bit synchronous up down counter here being used for the tracking the car number. Like we can see the state diagram on the left that it starts 000 and ends to 111, which is binary, which is decimal number is 0 to 7. And here we used 3-bit people register for some short memory of how many cars are entered and exit, and then it sends to comparator. That's from my part. Another part will explain my team member. Thank you, sir.
Hello, Assalamu alaikum. Myself Mithila Farzana Jui, ID 235522143. I will be presenting slide 13 to 15, data handling and display control. Slide 13 and 14 we can see register and comparator. To stabilize the data coming from our counter, we use a 3-bit PIPO or parallel in parallel out register. This holds the current count so it can be cleanly read by our 3-bit comparator. The comparator is the decision maker of the circuit. It takes the output from the register and compares it against our hard-coded limit of 7. It has 3 possible output. First one is A is greater than B. A is less than B, and the last one is A equals to B. In slide 15, 555 timers to manage the visual output. We utilize 555 timers. We have configured these in two different modes. Timer 2 operates in stable mode to keep the space available display active under normal conditions. However, when the comparator signals that the garage is full, timer 1 operating in monostable mode triggers the full display. This dual timer setup ensures the driver gets an immediate and clear signal at the entrance. Thank you.
This is Anirban Prothay. In this presentation, I'm starting from the next part, which is the FSM. The full form of FSMs is the finite state machine. In this slide, we created finite state machine for the control logic. We see the state diagram and the state table. In the state table, it defines exactly how the system transition from one state to the next based on the entry and the exit triggers. From the state table, we created the state diagram. From the next slide, we find the output equation from state table and the state diagram, which is translated to logic into Verilog SDL code. And the next slide, we see the Verilog SDL code. This allows the system to simulate it or even implement it on an FGA chip. The next slide, the drawbacks and the limitation. In this slide, we address the limitation of our current design. We identified the issues like fixed capacitor issues. We also identified that the sensor noise and the temperature sensibility in 555 times. To improve this, we recommended moving towards a microcontroller based on system. In the next slide, we see the replacing simple logic with the microcontroller, which we can see after the next slide, where we'll be replacing the microcontroller that would allow for advanced features like LCD displays, memory logging for security, and the automated billing. While this increases complexity, the reliability and the features it adds are well worth the effort. And that's all. Thank you, sir.